Good afternoon, folks. Want to start with a little review of what we talked about with inverse functions yesterday, and then add a little bit to that discussion. Talk a little bit more about some of the interesting problems with inverses that we'll run into. And if there's more stuff that you guys want to look at, let me know. But that's my plan for today. Let me pull out. So it was a kind of warm up. Take a moment and find that angle in radians. While you're at it, why don't we go ahead and say, call this question 1. We'll let question 2 be the find the sine inverse of -1/2. And then how about the cosine inverse of the sine of, let's go pi/3. Ooh, let's go with -pi/3. That'll be more fun. Okay, so I'll give you a couple minutes to play with those. Then we'll talk about them and make sure we're happy. And if anybody wants to confirm or argue with Garrett's question, Garrett, I do have a problem with that answer, actually. So if anybody wants to argue with or yes, Felix. So take a minute, try to find all those. Talk to each other about it. You guys know you can talk to each other, right? You can message each other. You can message in private to each other. Turn your mics on, talk to each other. (32 pi/80). They are the same. Yeah, I think 0.56 is probably perfectly fine for this. It is a little bit tough to actually turn back into radian measures for the decimal. But certainly a nice thing to be able to do. So yeah, and we could say 5.6 or 5.59 or round it. we should be able to round it to whatever level we want. So triangle. Let's see. Felix, you asked about 2 and 3 in radians. 2 doesn't specify one way or the other. So 2 could be in either degrees or radians unless specified. So I'll take either one for that. Number 3, the sine of negative pi over 3, that negative pi over 3 is in radians. So our answer should stay with that convention. If a problem is expressed in radians, we should answer it in radians. If it's expressed in degrees, we should answer it in degrees. So for 3, we really should be answering that in radian. For number 2, really either one would be fine. But why don't we go ahead and go with radians because everything else is in radians here. Two and 3 should have exact answers though, because they are versions of our standard angles. So for example, Martin 5 pi over 6 is an exact angle or exact answer. So that's good. Even that, quite beautiful, what was it, 8 pi over 45 is a beautiful exact answer, but I wouldn't tend to expect that for a problem like number 1 because it's not one of our standards. Oh, I got some argument about number 3. I love that. We always learn more when people argue and have to kind of, what the heck was that? You argue and have to kind of defend their positions on things. So always like when that happens. That is not where I wanted that to land. Why not X? Details. Details are always good to be careful with. So for that number 2, if we want that sine inverse of negative 1/2, we know negative 1/2, again, this is an inverse function. So in general, remember all of our trig functions, their job is to take in angles and give out ratios. So our inverse trig functions, they will do the opposite. They will take in ratios and give back angle measurements. So since this is an input into the inverse function, that negative 1/2 is a ratio. Because it's going into sine, it's a y value. So it has to be some angle where that y value is negative 1/2. So that would be, that would happen on our circles, for example, there and there. I've drawn that angle a little sharp, but that's okay. A little wide, but that's okay. So if we look at where that happens on our unit circle, it'll look like it happens at 7 pi over 6, and it will look like it happens at 11 pi over 6. But we know our restriction For sine inverse, we're only talking about angles between negative pi over 2 and pi over 2. So that would be between negative pi over 2 going up to pi over 2. So we have to give the version of this angle that is in that restriction. So the coterminal version of that angle that's in that restriction is the negative. So we can't use that one because it's not in the right quadrant. The 11 pi over 6 is in the right quadrant, but it's in the wrong version of that quadrant. So we've got to use the negative pi over 6. And we talked about those restrictions yesterday, but those restrictions are most of what makes the inverse functions a little bit weird. Now, number 3. I do recommend for all of these not as important as some of the ones we'll do later today, but if you can draw a nice diagram, nicer than that one preferably, but if you can draw a nice diagram for it, you're gonna help yourself a lot. So negative pi over 3 is down here. Negative pi over 3. So that yields a particular answer for sine. So this again is an angle. That angle's going into the sine function. So this is going to output some ratio. Now, luckily, because we know the sine of negative pi over 3, that's one of our standard angles, we know what that ratio is. We know that ratio for this particular angle is what the negative square root of 3 over 2, right? So we could even just say negative square root of 3 over 2. Now, we want to put that ratio into cosine. So if that ratio is going to go into the cosine inverse, the negative square root of 3 over 2. By the way, we don't actually have to know that value to do this, but it's nice if we do. This is a negative quadrant for sine, so we knew that sine was going to be negative, right? Because it's in quadrant 4. So this was going to always give, no matter what, a negative answer. We happen to know what that negative answer is, but even if this was, the sine of negative 1.3 radians, and we didn't, we'd still know it was negative. Because it's negative, when it goes into the cosine inverse, we know what quadrants the cosine is negative in. The cosine is negative in quadrants 2 and 3. So this angle would have to be somewhere in quadrant 2 and 3. But the inverse for cosine only knows about quadrants 1 and 2 because the cosine inverse is restricted between 0 and pi. So we're essentially being asked what angle in quadrant 2 makes cosine output the same thing sine did at negative pi over 3. So this length of negative square root of 3 over 2 would become this length. So the relationship between this angle and that angle, they technically have to be complements of each other for the y value to switch to the x value. So even if we didn't know that this was negative square root of 3 over 2, we could figure out that, that this has to be the angle in this quadrant that is has a reference angle that is the complement of this reference angle. Now that's a little bit more complicated of a logic than just being able to go, hey, where's negative square root of 3/2 for cosine? But let me know if that seems reasonable. See, Garrett, you said 7 pi over 6. 7 pi over 6 would be down here. And 7 pi over 6, you're absolutely right, does give the same negative square root of 3/2. But the inverse function doesn't know about that one. That's why we have to use the 5 pi over 6. Let's see. Felix, you were saying the x instead of the y, and you're right. We'd switch from the y to the x when we switched from sine to cosine. So playing with these restrictions, particularly when the functions are mixed together like this, can be a little bit sticky. Questions about any of those examples? For the most part, this is what we end up doing with inverse functions. We have ratios and we want angles. That's, a large portion of what we'll do with our inverse functions. But when we start having to do things that are a little bit more intricate, we have to be careful about these restrictions. And particularly when we start solving equations with the trig functions in them, and we start trying to mix our algebra logic with our trig function logic, those restrictions are going to become something we need to be super comfortable with. So it takes a little bit of practice, but it'll get there with that practice. So anything about these before we start looking at some other things we can do with these?
Hey, Matt, I have a quick question about problem 1 for you.
What's that?
Did you do the inverse of tangent 5 over 8 to get that answer?
Yep.
So I did the inverse of tangent 5 over 8 and got 32.005.
It's because you're in degrees.
Got it. Okay. That fixes it.
So that's also a correct answer for the angle, just not in the units we wanted.
Oh, gotcha. In radians, I see.
Yep.
Okay.
Okay, so let's look at, now, these are some of my favorite questions for this section. That's always a hint, by the way. If your instructor ever says, I like these problems, that should be like, okay, I'm going to learn how to do these problems. Even if they're bad, that means the instructor's going to do things like put them on tests and whatnot. I'll put negative. So we want to evaluate that expression exactly. So Felix, in an equation where we might want to use inverse to get rid of a trig function, that is exactly what we'll do. No idea if we ever want to do that. Yep, we'll do that a lot. How do we handle the inverse so we can see certain parts of the circle? That's, I believe, 7.2. No, chapter 7.3. So we will get big with that. It's a lot like having to put that plus or minus on when we solve with square roots. It's just a little bit more involved. So yes, we will absolutely do that. If you want to look ahead to 7.3 and get a preview of that, you absolutely can. So how are we going to approach problems like this? Hopefully you're getting used to the idea that drawing a diagram is going to be helpful. If not, let me try to convince you drawing a diagram is going to be helpful, because drawing a diagram is helpful. So if we're going to try to draw this angle or an angle with this ratio, or try to diagram this, the first question we need to find the answer to is, why I started writing F, is what quadrant is this happening in? We have to know that, because if we don't know what quadrant we're in, we're not going to be sure what's positive and what's negative. Because that might look like it's a -3 and a +5, but we don't know really if that's a +3 and a -5 or what. So, and we don't know about the other values in our ratios, whether they're positive or they're negative. So to be able to keep all that straight, we got to know what quadrant we're in. Luckily, there's only 4 choices. So do we think this is happening in quadrant 1, quadrant 2, quadrant 3, or quadrant 4? I'm going to give you 28 seconds. Got to vote for quadrant 2. Dan, you think it's in quadrant 2? Aren't there only 2 choices? Well, there are 4 quadrants, so there are technically 4 choices. We got to vote for quadrant 4. Somebody else who thinks it's quadrant 2. Somebody thinks it's quadrant 1. You're right, though, Felix. There are only 2 choices within the restriction, but that's part of the question. 1, 2, 3, 4. Got another one, a couple more for 2. Well, you changed your answer.
I cheated.
So we got 2 people that think it's in 1, 4 people that think or thought it was in 2, 1 person thinks it's in 4. Anybody out there not thinking? So let's look at what we know. So first and foremost, we're looking at the cosine inverse. And we know the cosine inverse is restricted. So the cosine inverse was restricted because the cosine function needed to become 1-to-1. So we restricted the cosine function between angles between 0 and pi. So it would be 1-to-1. So we could consider an inverse. So angles between 0 and pi are quadrants 1 and 2. So simply the fact that we're looking at cosine inverse restricts us to those 2 quadrants. The sine function isn't an inverse, so its restriction doesn't apply. So that's the first piece of information. And kind of like you said, Felix, that does restrict us to 2 possibilities within its restriction. Then I want to look at this ratio. The ratio, we're told, it is a ratio that's going to be coming out of a cosine function. The ratio is negative. So what quadrants is cosine negative in? Well, we associate cosine with the x values, and our x values are negative in quadrants 2 and 3. So according to the fact that it's an inverse function, we could be in 1 or 2. Because it's negative, we have to be in 2 or 3. The only place those overlap is quadrant 2. So we have to be in quadrant 2. For quadrant 1, it would have to have been positive. For quadrant 4, it would have had to have been a sine inverse as opposed to a cosine inverse. Now, this is one of the reasons I like these questions, is because they really make us put all the pieces kind of together at once. Makes them a little bit tough, but it really helps us think through how all of our little things interact with each other. So we know this ray is somewhere out in quadrant 2. All right, what else do we know about the ray? Well, we know the ratio we're told is negative 3 to 5. And that's a cosine ratio. So for cosine, we're told we know that that is our x over r, or if you prefer, our adjacent over hypotenuse. So if we want to consider this to be a reference triangle here, we know in terms of our reference triangle, this length is 3 and that length is 5. But Felix, as you're saying, we have to decide, let's see, wait, easier triangle with sides 3 and 5? Yeah, but because we're in quadrant 2, that 3 has got to be negative. Keep in mind our r values are a radius, so the r values are always positive. And then when we go to figure out that other side length, we know that that side length is going to be positive because it's a y value in quadrant 2. Again, that's why knowing the quadrant that we're in is so important. Particularly when we're dealing with tangent. And tangent, we don't have that radius, so the tangent can be, which one is negative and positive in a tangent is always a little bit weird. So we do want to figure out that other side. So the second thing we got to worry about is what is the missing value. Here we don't know this side length, so we got to go find that side length. So what's that other side length, or what tool are we going to use to find that side length? Guys are being very chatty today in the chat. I love that. So keep that up.
You can use the Pythagorean theorem, right?
Absolutely, we can use the Pythagorean theorem. So what, the 5 squared is negative 3 squared plus a squared, and solve that for a. Also, we've probably seen the 3, 4, 5 right triangle often enough that we might remember that that triangle exists. That is our primary Pythagorean triple. So if you happen to go, oh, wait, I remember that that's got to be a 4, then great. But if it's not nice like that, or when in doubt, Pythagorean theorem is good. So 16 is a squared, so we get a is plus or minus 4. How do we know whether to use the positive or negative? Because we know what quadrant we're in. If this was occurring in quadrant 4, that 4 would be negative, and the 3 would have consequently been positive. If we were in quadrant 3, they both would have been negative. So now we're left with, what is the sign in this scenario? Well, the sign is supposed to be the ratio between y and r. So what is the sine value when the cosine value was negative 3/5? Well, the sine value in that scenario, 4 over 5. So 4/5. You might remember kind of back in the day, like a week or two ago, we had questions that would say like, given or if the cosine of theta is equal to negative 3/5 and, say the tangent of theta is negative, then find the sine of theta, or find all the remaining functions, right? Or would tell you the angles in some restriction, and then find everything else. You guys remember doing those questions? This is exactly the same question as this, just in different language. So the cosine inverse of negative 3/5, well, that's the cosine being negative 3/5. Here we needed a piece of information because we know cosine can be negative in 2 or 3. So we needed the tangent being tangent being negative to tell us it was in solidly in quadrant 2. We don't need that anymore because the inverse tells us it's got to be in quadrant 2. And then, okay, what's the sine value? Well, the sine value, the little Pythagorean theorem gave us the 4/5. So this really is just an inverse translation of something we've already done into a nice little package. Find me the sine ratio when the cosine ratio is negative 3/5, respecting our inverse restrictions. That's what this question asks. Let's try that with a tangent. So let's say the tangent of the sine inverse of 2/5. That's always fun. So take a moment and find that tangent ratio exactly. Square root of 21 over 2. Maybe, I don't know, I haven't done it yet. So, looks like it's got some of the right numbers in it. So it's got the right sign to it. So it's got potential. It's not. Okay. Yeah, yeah. That might be squishy and hard to read, but it's a thought bubble. So thoughts are often hard to read. So we got a positive ratio for sine. Positive ratios for sine means it's got to be in either 1 or 2, because that's where sine is positive. But sine inverse is defined from negative pi over 2 to pi over 2. So sine inverse is defined in 1 and 4. So where are both of those things true? They're both true in quadrant 1. So this has to be happening in quadrant 1. So I'm not trying to draw this at any particular angle. I just need to make sure it's in the right quadrant. So sine is telling us the y over x. So the sine is 2 and 5. Now, technically, we could make these numbers, the 2 and the 5, anything we want as long as that ratio holds. So if you wanted your R value to be a 1, then you could have made this a 1 and that a 2/5. That would work. That's just the sine is our Y value when the radius is 1. That ratio is the same. Heck, you could have made this, if you wanted to for some reason, make that a 4, make this a 10. As long as the ratio holds, it doesn't matter. Probably the easiest thing to do is go good old, numerator to denominator. But as long as the ratio holds, it works. And some people really like that 1, so they'll put that 1 there every time. Fine. Then that's 1, and the Y value is a 2/5. Great. So that's up to you to find the missing side. All of our ratios are ratios between two sides, so there's always going to be a side that's not expressed. And we will always be able to find that side using Pythagorean theorem. So 25 equals 4 plus b squared. So b squared is 21. So b is plus or minus the square root of 21. And we know which one we have to use, what the plus or the minus, because we are in quadrant 1. So that length we know is positive. Hopefully you can see what happens when folks will sometimes draw the diagram, but not put it in a quadrant and just say, okay, that's this and that's this, and put the wrong sign on the other piece because they're thinking about the triangle, but they're not thinking about the quadrant. So do be careful about that. That quadrant is important. So we got that missing side, positive square root of 21. And then find the requested ratio. What ratio are we asked to find here? We're asked to find the tangent ratio. So given this information, the tangent of this angle, remember the sine inverses will equal angles. So it is the tangent of what, tangent of this angle, which is the angle that makes sine output 2/5. But it's going to be our y over x, or opposite over adjacent if you prefer. So 2 over the square root of 21. And Felix, you're right. You're like, I don't want to rationalize. Yeah. So 2 square root of 21 over 21. And technically, you turned it into cotangent by doing that. Because the cotangent is that thing's reciprocal. So. questions about either of those before I kind of make it bad? I'm going to show you a couple things that are a little bit more out there, well within the bounds of what we're supposed to be able to do, or will need to be able to do, but a little bit more out there. You guys all comfortable where all that's coming from? Do practice these. There's a couple of these on your homework. These are really common problems to look at and to watch us talk about and go, oh, those make sense. I'll be fine. And then when you're alone in the dark by yourself, you look at one of these and you go, wait, what do we do again? So be careful about that. Do make sure you put some practice into these. They will really help you kind of start connecting all the little pieces together. So make sure that that time gets put in there for these. But I do want to show you a couple of things that can happen. And Felix with with the reciprocals kind of brought one of those things up, and I think it's a great thing for us to look at. Let's say we had the sine of the secant of 7/3. Sorry, sine of the secant inverse of 7/3. Now, it's likely and even very reasonable that as soon as we see secant there instead of sine, cosine, and tangent, our reaction could very reasonably be crap. But I'll show you the lovely thing about inverse functions especially. What do we know about secant? How did you know? Yeah. What's the one big thing we know about secant? Very careful, Connor. Love that, but very careful. It isn't the inverse of cosine. That would be cosine inverse, right? It is the reciprocal of cosine. If you wanted to use inverse in that sentence, you could have, but you would have had to have said it is the multiplicative inverse of cosine. And you didn't want to say that. So it's the reciprocal of cosine, or reciprocals are multiplicative inverses. So careful about that inverse language, especially in this sentence, but frankly, especially in trig. So we know it's the reciprocal of cosine. So if this ratio there is a secant ratio, then we can turn a secant ratio into a cosine ratio by using the reciprocal ratio. That is all we have to do to change from secant inverse to cosine inverse. Because we're looking at the ratio, and we know secant's ratio is the reciprocal of cosine's ratio. So take the reciprocal of the ratio, and you've changed from the function to its reciprocal counterpart. So for secant, this would have been, say, our hypotenuse over adjacent in terms of triangles. Well, if we flip that, that's adjacent over hypotenuse, that's cosine. So don't panic when it says that. Go, ha, ha, he thought he'd trick me. And then positive and cosine inverse, so we're in quadrant 1. So that's a 3, that's a 7, that's what, 2 square root of 10. So the sine of that is 2 square root of 10 over 7, and boom, you're done. So keep that in mind. And that works, throughout. I've seen lots of problems, particularly happens a fair amount in calculus, where secant, you don't want to mess with secant in calculus. It does all kinds of horrible things, and particularly the inverse functions. But being able to just go, I would rather that was cosine, and now it's cosine, is such a powerful tool sometimes. Yeah, pretend you don't see the bad part. I don't want that, so change it. Get rid of it. Get the thing you don't want or don't want to look at out of the way. Now, we could certainly have done almost any of these problems, if not all of these problems, just if we didn't care about being given an exact answer, you could literally type sine of cosine inverse of 3/5 and hit enter, and your calculator will give you a very nice decimal approximation of that. I am, of course, always going to want these in exact values, so I'm going to want these. But for most practical applications, eventually that would turn into a decimal approximation at some point. So why fight so much or place so much about being able to do these in exact values? And I'll tell you why. Because in practice, you will almost never be asked this question. Because one, it's just a crank out a value question. And two, you're not going to be doing something that's quite that straightforward. What you're going to be doing is you're going to be simplifying stuff that looks like the cosine of the tan inverse of a variable. We're not going to have a nice value. We're going to have this, and it's going to be equal to something, or it's going to be part of some other big expression, and we have to solve for that x. I think the last question on your homework is like this. So you'll practice this a fair amount to get used to the idea, but then all of a sudden somebody comes by and hands you this, and it's like, well, what the heck am I supposed to do with that? Comes up a fair amount in calculus and physics in your first terms. So it is something, particularly calculus, your second term in calculus, a lot. So what do we do? Nice thing is we do exactly the same thing we did before. The first question is, what quadrant are we in? Well, tangent says we have to be either in quadrant 1 or quadrant 4, the negative first version of quadrant 4. And because we don't know whether this x is positive or negative, we don't know which one. But it's got to be one of the two. Fair? So it's either in 1 or 4. And for each of those, we could draw a triangle. Okay, what do we know about that triangle? Well, we know the tangent ratio is x. So the tangent ratio is supposed to be y over x, or opposite over adjacent. So this opposite side over that adjacent is x over 1. So that would be x, and that would be 1. The same thing we would do if it was a 5. If it was a 5, we'd say 5 and 1. I want that to be darker. We'd say, if this was 5, we'd say 5 and 1. It's an x. Okay, so we say x and 1. If that x was, say, a negative 7, okay, the negative would be down here. So there's also, a version of that x here and a version of that, well, same 1 there. Okay, so we got to find the missing side length. The missing side length is this hypotenuse. How do we find the missing side length? Well, we've done the same thing every time. We've done Pythagorean theorem. So that other side's got to be square, has to be x squared plus 1 squared. So our c is plus or minus the square root of x squared plus 1. Because it's a radius length here, it's got to be positive. If it was the adjacent length here in this quadrant, in both of these quadrants, the adjacent length is positive, so it would still be positive. So we're going to be able to pick which one of those based on the quadrant restriction we're in. Okay, last but not least, what is the cosine ratio for this scenario? Well, cosine is adjacent over hypotenuse, so the cosine is 1 over the hypotenuse, square root of x squared plus 1. So this is equal to that. Tell me that doesn't feel a little bit cool. So in practice, when you're using this out in physics, in engineering, in computer science, in most math as you go along, you're generally most often going to be doing this when these are either variables or variables and constants or even other expressions. I mean, this could have been an entire other function in there, and we would just do the same thing, g of x quantity squared. So it's very common to have to do this in much more gross looking situations. But the nice thing about those gross situations is the logic is exactly the same. Do what you would do if it was a 7. It just feels a lot cooler. Irrational denominator, 0 points. We could rationalize that if you really, really wanted to, but the rational version of that isn't, that's not helping anybody. We don't tend to rationalize functions. We tend to rationalize numbers. Questions about that?
Yeah, I have a question.
Shoot.
So this was kind of like almost a real life application. Like you're saying, in real life, we're not going to have all the answers that we have in these questions, right?
Yeah, in real life, you rarely have to do this problem where you actually have all these numbers and you're trying to find a number.
So in real life, how does that problem 1 over square root of x squared plus 1 like help anybody? Like it kind of seems like
trying to use your calculus tools on this would be probably a 20-minute problem. Trying to use your calculus tools on this, a 5-minute problem.
Okay, so we're kind of just making it easier until we get more information in real life, or
to do whatever you're going to do with it. If you're going to try to find its integral or a derivative, or find the area around it, or particularly trig functions, because trig functions are transcendental, they don't like to mix with algebra much. Yeah. So if you were trying to have this expression mix with other algebraic expressions, it doesn't want to mix. Turning it into this is now an algebraic expression, it can mix very well.
Okay, I get
it. It adds a lot of manipulation power to it.
Gotcha. I was just curious. Thank you.
Let's see, you guys know you have your, excuse me. You guys know you have your test tomorrow? Excuse me. Almost made it through the day without coughing too much. Was I? Yeah, you have your test tomorrow. You've either read the thing or we've talked about the thing where you're going to be writing out your work on scratch paper and then sending that in afterward. I know we talked about that in class a couple days ago. But so make sure you're doing your handwork nice and neatly so I can give you as many points as possible if things go a little bit off. Because of that, always please keep in mind that when you're done with the test, it'll say, here's your score. But that score is usually dramatically lower than it will be once we go through everything. So I almost want to recommend don't look at that score at all until they're done being reviewed. The phone app that is listed on the site is, I think it's called CamScan or CamScan. But really any PDF scanner or any scanner app should work. Genius Scan, I've had a lot of people use that. It works very well. I don't tend to use the CamScan here just because it's not the one I've been using for a while. I can't remember the name of that one. It might actually be Genius Scan. But let me see, which one does it say? Oh, there it is. Oh, it doesn't say it there. It says it in the actual testy thing. Oh, it's in the test scratch paper thing. I knew it was there somewhere. There it is. Yeah, Cam Scanner or Genius Scan are both listed there. But really, any scanner software will work. I had somebody who couldn't figure out how to get the phone scan app to work, so they just took photographs of them and sent those. That works too. The big thing with that is the scanning software can generally keep it all as one document. So we'll ask you can scan page after page. Hopefully it's not too many pages, but you can scan a couple different pages and it will make that one file that you can send. If you're taking pictures, the multiple pictures will have to be sent as different files. But what you can do, where it says choose file, upload one of them and it will ask you if you want to then it'll say you've uploaded this. You can then upload another one and another one and another one. It will show me all of them. It'll show me this is the last one they sent in, but here are all the others. So if you have like worst case scenario, if that's what you make work, make that work. I had somebody really panic and sent it to me, like wasn't sure if it was working and sent me her photos as an email. Fine, that worked. So. Yeah. And I think I had all but one person, it worked fine that day. The other person had to talk down a little bit, but we got theirs in too. So it generally works. And if it gives you any trouble, don't freak out, don't panic. Let me know. Send me a message, and we'll figure it out. Okay, I'm going to be around today and tomorrow. I'm not going anywhere. Nobody goes anywhere, right? So if something comes up while you're practicing and getting ready for that test, let me know. And have a wonderful day.
Hey Matt, while I have you, I just had a quick question about the unit circle.
Okay.
So
before I answer that, let me show something to Dominic.
Oh yeah, go for it.
He asked something in the chat, and want to make sure he gets that answer. So, Dominic, when you go to the Friday where it says the test scratch paper, if you hit the link for that test scratch paper, it gets you to this assignment where you can upload the work. So you just choose file from there, and wherever it's stored, if it's on your phone, you can load up MyOpenMath on your phone and do the same thing. Choose file wherever that file was stored on your phone, link it, and open, and it will download it directly there. You're very welcome. Connor, what were you asking about the circle?
Yeah, I've just been using it pretty heavily in all the homeworks and stuff like that. And I was just wondering, is that something that would be really beneficial for us in the future going into our careers and things like that to memorize and have,
Yes and no. I say no because I don't memorize anything. Try to memorize as little as possible anyway.
Yeah.
But being able to build it and or see it, yes. And that's one of the reasons that when I've talked about it with you guys, I've talked about it from the perspective of all that counting, right? Where we've got that pi over 4, and then we can count around 1, 2, 3 pi over 4 and all that, and have those triangles so we can go, okay, the triangle is there, so that's what these values are. The triangle is there, so that's what those values are. So instead of memorizing the whole thing, you're memorizing the pieces that built it and then being able to build them, if that makes sense. As opposed to, I've had people who just raw memorize all of them. You have no idea where they're coming from, no idea about the triangles that are in there. They just have memorized every single one of those. And that's a lot of extra work. And it's not as flexible. Fair? But
Okay, that answers my question. I just was like curious. I'm just using it so often that I wondered how reoccurring this is.
all the if you're going into physics, engineering, math, calculus, you're going to take calculus, you're going to do computer science, you're going to do it becomes the unit circle becomes a friend. You should construct yourself a very nice one, put calligraphy on it, have it laminated, keep that in your back pocket at all times.
Okay, that's what I figured. So I'll do just that. I'll get real comfortable with it.
Cool.
All right, thank you so much, Matt.
You're very welcome. Samuel, anything you need?
No, I'm good. Thank you.
Sure. Martin? Is there anything else you need? Anything I can do for you? Anything that would be helpful? Okay. Well, if you guys come up with anything you need between now and your test, let me know. And I'll see you Monday, if not.